Hey guys, so the point of this video lesson is really more about the calculations involved with acid and base titrations. However, I do want to quickly run through what is in your notes about titrations. You did titrations last year. Remember, it's one with the burettes, the Erlenmeyer flasks. A couple of things to note. You see on there the things you need and the steps of the titration, but a couple of important things. First of all, typically the standard procedure is to put the base in the burette and put the acid in the flask, regardless of which one you know and do not know, because the point of a titration is to find the concentration of an unknown, which might be your acid or your base, but you still want to put the base in the flask and the acid, oh, I said it wrong, you want to put the base in the burette, B, base in burette, and acid in flask. And then your indicator goes in the flask with your acid. Okay. Also, what's happening when you do a titration is essentially you're doing a really carefully controlled neutralization reaction. You're trying to neutralize all the acid in the flask with some base, and that's the point of going so slow right there at the end point, is to make sure that you haven't tremendously overshot the end point. And we use an indicator for that. After we go over the math, I'm actually going to tell you about another method that's a little more effective than even an indicator that we will be looking at during our lab time together. So that is what's happening. Key terms, you see the term equivalence point. Equivalence point is the point where the acid and base have neutralized each other, so that's the equivalence point. There isn't this written on your paper, so you might want to jot it down, that the end point is the point where all the acid, the end point is where the color change occurs in the flask. So like when you're using phenolphthalein, when it goes from clear to pink, then you have reached the end point. So ultimately, you want your end point and your equivalence point to match up. That's the important part. All right, so for calculations, you notice you're given an acid and a base in your problem. So the very first thing you're going to have to do is write the chemical reaction for that. So we have H2C2O4 reacting with NaOH to make Na2C2O4 and H2O. And you have to be able to do your own acid-base reactions. We already studied that. So if you need help, please let me know. They also have to be balanced, because anytime you use an equation for anything, you need it to be a balanced equation. Then what I like to do is isolate my information. So if you go through the problem, you find that they told us that we have a 25 milliliter sample of this, and that we have a 34.47 milliliter sample of this with a concentration of 0.485 molar. It makes it a lot easier to tell what to do, because it's obvious. Oh, I'm sorry, let's write down too that we want this molarity. If this is what we're trying to solve for, is the acid, then we have to start with the base. So you're going to take this information that you've been given about the base, so I'm just going to label this that it's base, and you're going to use the molarity equation. Molarity equals moles over liters. So you're going to do 0.485 equals your moles, which we don't know how many moles we have, over 0.03447. This is just like the problems you were doing the other day. Actually, there were some titration problems in the problems you were doing the other day. Just a matter of looking at what you have, converting it into things that you can use. Moles will be something that we can go from NaOH over to the acid. So when we cross multiply this, you end up with 0.016718 moles of NaOH. Now, in order to find the molarity here of Hc2H3O2, of H2C2O4, we are going to need to know the moles, and we know the volumes given in the problem. So my next step is going to be to convert from the moles that I just got, 1718 moles of NaOH, into moles. So I'm going to go from moles of NaOH into moles of H2C2O4. And I need my coefficients for that. So I look back up. I've got a 1 for the acid and a 2 for the base. So I'm going to divide that and find that I have 8.359 times 10 to the negative third moles of H2C2O4. So that's my moles now of my acid. Now I'm going to do my acid. Molarity equals moles over liters. I know the moles of my acid is 8.359 times 10 to the negative third divided by the volume of my acid, which I have up, oh boy, sorry, hit the wrong button. There we go. Which I have up here at 25 milliliters. Milliliters needs to be in liters, so it's going to be 0.025 liters. I'm going to divide that, and I find out that my molarity of this acid must have been 0.334 molar. So again, it's what we did the other day. You're going to look at what you've been given, and I recommend for those of you that are having trouble with deciding how to do these problems to write your stuff in like this, because it allows you to see exactly what you know and what you don't know. And you always want to start with what you know as opposed to what you don't know. Okay, so that's one problem. Let's go ahead and try another one. This one is acetic acid. You notice I just kind of look at the problem and I assess that it's an acid-base reaction, and I'm just going to start by writing my information. I don't even really have to look and see what it's asking me to do, because I know I'm going to need a balanced equation. So my salt and water form looks like that. It's actually balanced already. Coefficients all ones. I'm going to write down what I know. I know that I have 25 milliliters of my acid. I know that I have 28.33 milliliters of my base, and that it's 0.983 molar. And I know that I'm trying to find this molarity. So again, stay away from the one that you don't know yet. It's clear we're going to use the acid last here. So we're going to start with the NaOH. You know that molarity equals moles over liters. So molarity is 0.983. We don't know our moles. I'm going to put this volume here in liters. I'm going to cross multiply, and that's going to tell me how many moles of NaOH I have. So I have 0.026998 moles of NaOH. Now I like to do the next step just right there along with that, because the next step, if I know moles of NaOH, I can find moles of my acid. So I'm just going to add a little conversion on here, and I'm going to say moles of NaOH on the bottom. I'm going to say moles of H2C2O4, 1 and 1. When you multiply those, obviously it comes out to be the exact same number as you had before. So you're multiplying by 1 and dividing by 1. So this is moles of, did you see that? I messed that up. There you go. See? Okay, now moles of our acid. Okay, so that's not our final answer though. We want molarity. So we have to go back to the information we know now about our acid. So our acid is acetic acid. I always kind of label my work this way just to make it clear as to what I'm plugging in for right now. And if you do something similar to that, it will make it a lot easier for me to grade your paper, and if you make a mistake, to give you partial credit, because it'll be clearer to me what you do and don't know. So 0.026998 over the volume of my acid, which I need to go back up here. My volume of my acid is 25 milliliters, so I got to put that into liters. So when I plug all of that in and I solve, I find out that my acid's molarity was 1.08 molar. So again, these problems allow you to take one substance that you do know the concentration of, do a titration so you get both the volumes that you need, and then ultimately figure out the concentration of another. This problem also has one more extension to it, which actually we're going to do something similar in our lab, and it actually wants us to calculate the mass of the acetic acid that's in that solution. So if you think about it, you already calculated the moles right before we got our last answer there. We found out that we had this many moles of acetic acid, and all of you are capable of converting from moles to grams. So that's really all this problem wants. So in every 1 mole of acetic acid, there are 60.0 grams. When you multiply that, you find that in this solution that we used, this 25 milliliters of 1.08 molar solution, there were 1.62 grams. And again, in our lab, we're going to be doing that as well. So, important part of the math. Now, if you look at the back of your notes, you're going to notice there's one more little section there about pH meters. pH meters. pH meters are another great way to be able to figure out what the equivalence point is and do your calculations. It's actually a more accurate way to do a titration. In order to use them, though, you have to have a little bit of basic information about something called a titration curve, which is what you see in front of you and on your paper in front of you. One of them is a little light on your paper, but you should be able to still see it. The important things, and we're going to learn a lot more about titration curves later, but you do need this introduction because we're going to be doing one in our lab. What happens in a titration curve is the pH meter is actually recording the pH at certain intervals, whatever intervals you choose. And so then all the data is plotted. And what you find is as you start to add, so this is the pH of your acid at the start, notice that it's very low. Okay, so this actually, you can make this note on your paper, is that this is a titration curve for a strong acid, strong base. And the way I know that is that when it was all acid down here where I put this blue dot, notice how low the pH was. So it's a very strong acid. And then it's ultimately going to end up at a very high pH up here once I've way overshot my endpoint, and so I know it's a strong base. The second one you see here is a weak acid and strong base. Notice that the pH starts higher, starts at an initial pH around 3. So that's an indication that tells you whether or not you're dealing with a strong acid, strong base or a weak acid, strong base scenario. So as you're adding it, you notice the pH only changes a very little. Okay, this is when we were doing our titrations and we were putting our solution in, you weren't seeing any color change during all of this. It is actually changing a little bit, but not a lot. This is where all the H plus is being used up. And then all of a sudden, you reach the point where one single drop changes the pH on this graph from about a pH of 3 all the way up to a pH of almost 11, a little bit over 10. That's why that one drop is so important, because it will drastically change it, and that's why some of you have said, well, if it's pink, then that means it's now too much base in there. But it's not that it's too much base, it's just that it happened so drastically during that segment that we don't have to worry about the fact that it went over a little bit, because it did happen during that exact same drop of solution. Now, then this, with pH meters, we usually continue on even past our equivalence point. So up here during this whole segment, it would have been really pink, because now we have way too much base. But in those titration curves, we actually curve the whole thing. So we start off where it's all acid, we show it adding base, we show where it's been neutralized, and then we show it going off into basic land because you continue to add base. Now the way you find your equivalence point is really easy. This jump that we saw happen, you go right to the middle of it. Okay, right in the middle of that big jump is your equivalence point. So for this one, notice if you follow your equivalence point over that it happened at a pH equal to 7. Now that makes sense, and we will get into this more later. This is on your notes as well. Second bullet there on your notes is that a strong acid, strong base will always make a completely neutral solution. It will have a pH of 7. If you look at the other graph, I want to show you that if you're not dealing strong acid, strong base, that won't happen. So same thing as last time, you are adding base. Right here is where it would have turned pink. With that one drop, it jumps up, and then it goes back to being basic because you continue to add your base. Notice the equivalence point is halfway up, but this time if you follow it over, the equivalence point is somewhere in there, maybe 8.5 or 9, somewhere like that. So let's just say the pH on this one was 8.5. That is not neutral. That is a basic pH, and the reason for that is when you take a weak acid and you mix it with a strong base, the base is dominant. Okay, the base is stronger than the acid, and therefore you end up with a basic solution, and we can see that in this graph. Now we're going to get more into this part later. Okay, for now I need you to be able to look at a titration curve and identify where the equivalence point is and be able to identify the difference between the two. Again, we saw this one started with a very low pH. Typically pHs under 2 are strong acids. And this one started down here with a higher pH, so that was going to be a weak acid. And we're only going to do combinations with strong base for now, so it's really a matter of just identifying that acid. And you should be able to look at the equivalence point and tell the pH off that equivalence point. And we are going to do that in our lab. Now, down at the bottom of your paper, there is a link to a video. It's okay, it's not the best in the world, but it does show you measurements and different things, and I believe it's super, super short. So if you want to take a look at it, it wouldn't hurt. It'll also familiarize